All right. So yesterday we ended here, and I want to start from here just to kind of, because I was rushing towards the end. But we went through the whole integration process, and I'm going to go give you a nice step-by-step process. We're going to do a few more of these types of examples. But we determined that the electric field strength at this point, at the center of a half circle of charge, positive charge because the electric field lines are pointing away, right, is given by 2 times Coulomb's constant times the charge density lambda divided by the radius of the half circle. Right, the radius here. Right. Now, remember that before we got here, at the beginning of this problem, we defined our charge density. And just like when we did centers of mass and rotational inertia, we talked about mass density then, but we're talking about charge density now. We can write the macro version and the micro version. That's one way of thinking about it. So the macro version is just charge divided by length. Total charge divided by total length. The length of this guy in terms of r is just pi times r. Right? So we could write that. Are you with me with that? With me on that? And then the microcharge density is, again, charge per unit length, but when we zoomed in on the micro scale to figure out the charge dE due to charge dQ, well, that charge dQ resided on a small segment of the charge, of the overall charge distribution that had a length that, if you remember your geometry, that's an arc length on that circle, and that arc length is the radius divided by the theta, or divided by the radius times the angle. In this case, that angle is d theta, right? We can say that up until dq, right, that angle is going to be theta, and then, well, the angle subtending the segment that the charge is located on would be d theta. Why d theta? Well, it's just delta theta, right? We go theta minus initial, theta final minus theta initial is delta theta. But if that delta theta is infinitesimally small or approaching infinitesimally small, then we call it d theta. Okay. And so our charge density on the micro scale is just dq over r d theta. And we have to do this because the integral is always going to be in terms of dq, but we can't integrate with respect to dq. We have to integrate with respect to some variable that varies as we go along the problem here. Okay. Now the thing is that whenever you get to a result like this, if you have an actual total amount of charge, in this case it's some unknown quantity of charge, q, we don't want to express our electric fields in terms of the charge density. We want to express the electric field in terms of overall charge, right? The charge that's actually present on the object. And so that's when we can go to the macro and get the expression for the charge density in terms of the total charge present, which is q over pi times the radius. And so we can substitute that in for lambda here, in which case we would get the electric field strength is 2k over r. If you're not good with compound fractions, you could do it like this, times lambda, which I know is q over pi times r. And then so I can say that the electric field strength at that point is going to be 2kq over pi r squared. And when you're doing quest assignments or multiple choice questions on AP Classroom or wherever we're going to be doing them, sometimes k is in there, sometimes k with a subscript e to remind you that that's not a spring constant, that's the electric constant, Coulomb's constant, or it could be 1 over 4 pi epsilon naught. Okay, so just get used to seeing both of those, so I'll kind of be using those interchangeably. If I wanted to express the true value for the electric field in terms of its vector nature, well, if I'm using the standard Cartesian coordinate systems here, I would have to say the electric field vector points in the negative j hat direction, negative j hat direction, right? So that's how I could express that in terms of its actual vector. Okay. Now I want to take this opportunity to just kind of bring us back, because when we solve problems like this, and as we'll see, we'll get even more complicated ones, determining these electric field strengths, we can get kind of lost. We can get kind of lost in these weird. Some of the expressions that we get for the electric fields can be pretty complicated looking, and we get kind of lost in that. I know I did whenever I was learning this stuff, and you kind of lose track of where this all stems from. And not only just this, but electric forces in general, which, as we pointed out, as your chemistry teacher might have pointed out, the underpinning for all chemical bonding, all types of chemical bonding, or electric forces dictate that stuff. The electric forces that essentially dictate how our power grid works, how electrical energy is delivered to us, and how we use it. All of that stuff we can trace back to one single concept, including this. Again, we tend to get bogged down when we're doing all this stuff. We're going to fill up the board with the problem that we're going to do today, and there's going to be all kinds of nonsense everywhere. But it all is dictated by Coulomb's law. All right, let's say I have two charges. Two charges that are separated by a distance r, which I'll actually draw as the position vector, the position of one object relative to the other. I have one charge, let's just call him big Q, and one charge little q. And all this crazy stuff that we're going to learn about for the rest of the year, even when we get to magnetism. When you learn about do you guys know what causes magnetism? Does anyone know?
Magnets.
What causes magnets?
Magnetism.
Isn't it just like atoms that are lined up in the same direction?
Yeah, kind of, yeah. But you don't have magnetism without moving electric charges. You cannot have, and so when you're talking about atoms lined up in the same direction, you're talking about electrons with the same spin orientation, which isn't spin like you actually normally think about spin. It's quantum mechanical spin. I don't really understand it, so, but it's motion. It's motion. You can't have magnetism without moving charges. You can't have moving charges, or at least accelerating charges, without electric forces. So everything, power grid, chemical bonding, everything we learn about for the rest of this class, all traces back to Coulomb's law. And Coulomb's law is as simple as this. The electric force between these two charges is directly proportional to the product of the two charges. This is easily determined in a lab. The electric force is also inversely proportional to the distance between them squared. And we can tie those two proportionalities together in Coulomb's law, which again looks just like Newton's law of universal gravitation. It's Coulomb's constant K times the product of the charges divided by the distance between them squared. Coulomb's constant is just there to tie the proportionalities together into a nice equation that allows us to calculate real stuff. And then again, you can replace K. Both of these are on your formula sheet with 1 over 4 pi epsilon. No, if you want to write it that way. When we get into Gauss's law, you'll see that it's actually sometimes more convenient to write it as 1 over 4 pi epsilon naught. And epsilon naught is a more fundamental constant than K. K is in terms of another fundamental constant. 2 actually, because pi is a fundamental constant. Not a physical constant, but a numerical one. All right. And then notice that we got to our general equation for electric field. Let's say I want to know the electric field strength at this location. Well, all I have to do, well, first of all, let me draw the force. This is the electric force that we just wrote the equation for. If it's a positive charge, that electric force is in the same direction as the electric field at that location, which gets the symbol capital E. If it's a negative charge, it's the same magnitude of force. If it's the same magnitude of charge, it's just the force is in the opposite direction, and it points in the opposite direction of the electric field line. But how do I calculate that electric field? Well, all I need to do is divide the electric force at this location on this charge by the amount of charge itself. And that tells me the electric field strength, which I like thinking of it as the number of newtons of force per coulomb of charge that I would actually place at that location. And so all I have to do is take the electric force equation. Oop, forgot the K, or R squared. And I'm just going to divide both sides by Q, little q, the amount of charge there. Q's cancel there, and this is what we define to be the electric field. The electric field is force per unit of charge, or the force divided by the charge present, And that's just KQ over R squared.
Okay, that makes a lot of sense.
And this is what we used yesterday when we determined this electric field. The only difference is that instead of having just the point charge, we had a little tiny charge dq, which we treat as a point charge, but then we just have to add up the electric fields generated by all those little tiny point charges and do an integral, right? So yes, it's more complicated, obviously. Obviously, it's more complicated. We get an expression that's very much not like this. The units are equivalent. If you work out the units, they'd be the same. So it doesn't look like that, but notice we got an R squared there. We got a Coulomb's constant. We got a charge, right? So the units will work out. They'll be the same units. Yes, it's more complicated to do this. We have to use our brains a lot more than just using Coulomb's law and using the algebraic version of the electric field equation. But this is no different. This is no different fundamentally. It's just in practice it's more difficult because we got to use more rigorous mathematics.
It's just like, so it's similar to like rotational inertia, how it's always going to be something mr squared.
Yeah.
It's be something
Yeah.
q over r squared. Okay.
Yeah. Uh-huh. So cool beans? All right, because we're gonna do it much more difficult. Well, not much more difficult, but note here we had some nice symmetry, right? We're always gonna have some amount of symmetry in this class, but whenever you go to like junior, senior level physics classes in college, electrical engineering classes, when you start doing really third semester calculus in college, then you'll learn methods where you can deal with situations that aren't very symmetric. Recall that when I put Maxwell's equations up here, I was like, these complicated looking equations, the integrals are actually the easiest part of the problems that we use Maxwell's equations for the most part. Because the high symmetry, the situations will be very symmetric, and those integrals will actually be very easy to do, for the most part. Not all of them, but most of them. So just keep in mind that you always want to be thinking, well, where's the symmetry in this problem, and how's it going to make my life easier? It made our life easier here because the point that we were interested in the electric field strength was equidistant from every single dq. All the infinite number of infinitesimally small dq's, the point was equidistant. If that point is not equidistant, well then it's going to be a little trickier. But it's all going to boil down to the same thing. Find the electric field due to that charge dq, and then set up an expression for it, and then do an integral so I can add up all the electric fields due to all the dq's. And then add them together, and then that gives me my total electric field. But like we noticed here, the x component of the electric field, or the x component of all the electric fields, because technically this was the y component. The actual electric field looks like this, right? It points this way. This is the electric field due to dq. I should be writing dE. But the x component of that dE is going to be compensated by the x component for the electric field generated by that dq. So that symmetry there tells us I don't even need to worry about the x direction. And on the FRQ, if you had to do this on the AP exam, you could just write, by symmetry, the electric field in the x direction is 0. And that's fine, right? You don't need to elaborate on that any more than that.
Okay. Just move that point slightly and make it 1,000 times more complicated problem.
Yes. 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 And you won't see that in this class.
Bump it up like half an inch.
Yeah, if you just take that guy and put him there, it's much more complicated. Much more complicated. Okay. How's Moonlight Sonata coming? We got down yet?
For what instrument?
For piano. I thought you were learning it. Third movement?
Oh yeah, no,
You don't have it yet?
I haven't pursued that.
Oh, I thought you said you were trying.
Well, I looked at it like once.
Oh, okay.
I just had been busy. You lied to Mr.
You've lied to me. People overlook it. The second movement, the first movement I think is kind of boring. The second one is great. And the second one I think is a lot, I don't play piano, but if I did, I would think that the second one would be a lot easier to learn. And I like it, maybe not as much, but I think it's really good. First one's kind of boring.
You did lie to Mr. Graham, but it's okay because you lied to us by saying that gravity is a force.
This
And that
entire
this
class
physics
is
is
just
true.
lying.
Everything's a lie. Everything I tell you is a lie.
Everything in this class is not true.
He's lying to us right now.
Okay. So I'm gonna give you just the steps to determine the electric field due to extended charge distributions. These are general steps. And these will apply to situations where you don't have symmetry. You'll just need a little bit more mathematical sophistication, which you'll get in college level courses in physics and specifically third semester calculus. But essentially, and we already know this, it was techniques that we've used already, but I just want to, write this out here. You divide Q, whatever charge Q, into how many? An infinite number
Of infinitesimally small.
can I spell infinitesimally? I don't know if that's how you spell it. Small DQs. Right? You don't want to draw all of the infinitesimally small DQs on your diagram, though, because that would be silly. So you draw a, put this in quote, representative DQ on your diagram. Right? Step one, draw a diagram. Right? I'm not even putting it there because that's fundamental. Draw a representative DQ. And whenever you start learning about integrals, if you haven't already, you'll be talking about representative rectangles. Right? Right?
Yeah, that makes sense.
Okay.
That's what you said before.
That's what who said?
You.
Oh. Yeah, but I don't teach calculus.
You should.
No, I don't know calculus that well. I know the calculus that I need to do this class.
I was about to say, since the teacher of calculus-based physics.
Now, there's a lot of stuff that I've forgotten that you have to know for that exam. I don't know if I want to learn it again. Okay, so you draw a representative DQ on the diagram, and then you determine an expression, or an equation, I should say equation, for the electric field generated by that DQ. That equation will have DQ in it. So you'll have to substitute. And as we'll see in the next example, we're going to have to make multiple substitutions in order to make the integral doable. Substitute to make the integral doable. And then 5, integrate. And get your answer.
Simple as that.
Simple as that. Simple.
Use math to solve the equation.
Use math. Yes. Use math.
You could almost make all those start with D. You could be like 4 make it doable, and then 5 do it, and then it's determine
Steps
draw.
Oh yeah. Oh yeah.
Steps to determine electric field due to extended charge distribution. Step 1, do it. Step 2, idiot.
Step 1, read the manual. Step 2, do it. Step 1, read the problem. Step 2, pay someone else to do it for you.
Well, when you're rich, you can do that.
Yeah.
Step 1, bribe the APs later.
That should be step 1, but only if you're incredibly wealthy and can afford.
I'm gonna be
My
so
retirement.
rich that I'm gonna become an engineer and then pay somebody else to do my job.
There you go. That's smart. All right, so you got that down? I'm gonna erase it so I can have the whole board. Okay.
No, wait.
The 5 Ds!
5 D's of determinant.
Okay, so we're gonna find the electric field. Generated by a line of uniformly distributed charge. But But always have in the back of your mind, like this is going to get kind of complicated looking, but have in the back of your mind, it's Coulomb's law. It's Coulomb's law divided by charge to get the expression for the electric field. We're going to find the electric field due to one little tiny point charge, dq, and then we're going to add them all up, and that's going to be our result. Okay, so the expression is going to look complicated at the end. It's going to look gross, but it boils down to that. It really does. So I'm going to draw.
It sounds a lot simpler than it is.
Yes. So I'm going to draw my my line of uniformly distributed charge. I'm going to superimpose my Cartesian coordinate system. There's my x direction, my y direction, and I want to find the electric field at some point P that is right aligned with the middle. Again, if you take that point and you move it a little bit, then it's going to get more complicated and you won't see that in this class. So it is cutting right through the center. And so this is the origin right here. And this is, I'll call it just L over 2. We'll say that the total length of this rod is L. And so it extends from negative L over 2 to L over 2. So note, we have some symmetry here, right? We have some symmetry. The point is going to be equidistant from the corners, or the ends of the rod. Okay. And from that symmetry, I can already tell that the electric field in what direction is going to be 0.
Why?
The x direction is going to be 0. Because if I draw my representative charge dq right here, it's going to create an electric field pointing in this direction, right? That's my electric field dE. It's not a straight line. But I also have a dq over here, which is going to generate an infinitesimally small electric field dE pointing that way. And that x component and that x component are going to cancel. And so I can make the statement by symmetry. Is there 2 ends in symmetry?
At least
If you make it that way.
By symmetry, the electric field in the x direction is 0. Right. Okay.
By making it a little bit to the left or the right, you get now an X direction that makes everything more complicated.
Yeah. And so that's why we start with nice symmetry. But notice, though, that the distance from dq, all the dq, is not the same as it was with the semicircle of charge, right?
the one way you could also do this and be a weird but interesting way to calculate is if you had a point in line on the x-axis.
What? Oh, like over here?
Exactly.
We'll do that. You'll do that. Okay. Now to make sense of this, and to go, so that's my representative charge dq. Drawn the electric field dE. Now I need to write an expression for that dE, right? And so I need to label my stuff here. So let me go ahead and just label some things. First of all, I know that the electric field that I'm looking for is going to be pointing this way, right? That's my dE in the y direction. So that's the component. That's the vertical component of dE. So I'm going to need this angle here, which I'll notice is congruent to this angle. I know this P, point P is along the y-axis, so I can call this distance here, or draw this position really. It's a vertical height y above. I need to indicate the position of dq on the x-axis with a position vector d, or the position vector x. dq itself, if I take x final minus x initial, I get delta x, right? You get the segment. This length minus that length is that length. But because it's infinitesimally tiny, that's a little tiny dx. Remember that dx is what we got to change dq. We got to express dq in terms of dx because we can integrate with respect to dx. We can't integrate with respect to dq. So just like on the semicircle of charge, we don't have rd theta now though, right? We just have the charge density is going to be dq over dx. And then this distance right here is actually r. right? That's the distance r in our electric field formula, kq over r squared. That's bugging me. All right. So why this position vector x? Well, we need to denote the position of dq. Right? And we denote that with the position vector x. And then we've indicated the position of this guy, and that guy resides on a small segment of the line of charge, and that segment has length dx. All right. So I've got my diagram, and you'll see why we need this diagram as we go through the mathematics. You'll see why trying to do this problem without labeling all this stuff would be very difficult to do. I'm recording, right? Yeah. Before I go on, are we dealing with linear, volumetric, or area charge density? Linear charge density. Technically it is a volume, but we just consider it to be very thin rod of charge. So we have on the macro scale, it's just total charge Q divided by total length L. On the micro scale, we have tiny charge dq divided by the tiny length dx. And again, dx in this case is not going to be r d theta because it's not a circular arc. It's just a small segment, straight line segment of wire, which lets us solve for dq in terms of dx rather easily, actually, right? When I see dq, I can just replace it with lambda dx. All right. Get used to doing that. I like doing that right in the beginning, writing my charge density equations, because I know I'm going to have to use them. I know I'm typically going to use this one to change the integral to a form that I can actually integrate, and then I use this one to simplify my result at the end. Okay. All right, now I got all that drawn. I've got my representative charge. Now I'm going to write an equation for the electric field generated by that representative charge, dq. And that's going to be the dE, the differential electric field. But remember, all the x components cancel out, so I actually want to compute the differential electric field in the y direction. And I'm going to go ahead and use k here instead of 1 over 4 pi epsilon naught, just to keep it condensed down a little bit. So that differential electric field is going to be k times dq over r squared times what? It's a component. We're looking for this component.
Oh, yeah,
Who said sine theta?
Cosine.
Cosine
That's what I said.
theta.
You didn't hear the cosine.
Oh, gotcha. Now, when we do an integral, until you learn how to do double and triple integrals, which have fun with that, if we're doing it as integral, then we can only have one variable that varies, right? If you have more than one variable varying in an expression that you're trying to integrate, you can't do it. You can't do it because you can only integrate with respect to one variable. Does theta change as I integrate across this rod?
Yeah.
Theta changes. Does r change as I integrate across this rod?
Yeah.
Yeah. And so I gotta be careful here. I gotta rewrite this. I gotta make some substitutions.
You need to rewrite R and cosine theta.
What's that?
You need to rewrite R and cosine theta.
Yes, absolutely. Very good. Then we also need to substitute, obviously, dq. We need to solve this for lambda dx. Yeah, we need to rewrite r and cosine theta, because what are we probably going to be, what variable do we need to integrate with respect to? X, right? Because we have our charge expressed in terms of dx. Our charge dq expressed in terms of dx. So as Bradley pointed out correctly, we need to rewrite r and cosine theta in terms of x, and if there's anything else, they need to be constant, right? So let's do cosine theta first. How can I express cosine theta in terms of x?
Well, there's
Actually, let's do cosine theta after. Sorry. Let's do r first. How can I write r in terms of x?
It'd be square root of y squared
squared plus x squared. Right?
Yeah.
Yeah. Pythagorean theorem. R squared equals x squared
Oh.
plus y squared. Square root both sides. I don't know if you've gotten there yet in calculus. It's called Pythagorean theorem.
I'm not sure, Mr. Grant.
Yeah. It's pretty advanced stuff, but eventually you'll get there. So there, I can write r in terms of x. That's good. And then y is a constant, right? Y doesn't vary as I go across, as I integrate across the rod.
Oh.
And then so with that, I can take cosine theta. Well, what's cosine theta? I got these vertical angles here. They're congruent. What? Not x over r, that's sine theta. Y over r. And again, this is why I did r first, because r varies and
Y
x,
squared, square root x squared.
so we can rewrite cosine theta as y over the square root of x squared plus y squared. And again, we got this substitution here too that we need to make. So throwing all that junk in there, I get that the differential electric field in the y direction will be k. dq I replace with lambda dx. R squared. Now, if r is the square root of x squared plus y squared, what's r squared? What?
All that squared.
X
Oh,
squared
shoot.
plus y squared.
X squared plus, it's just x squared plus y squared, right? Now we are going to be multiplying this by something, so I'm going to go ahead and put that in parentheses because that's just these things. But then we got the cosine of the angle, which I also, and we'll see. You'll see it. You don't need to do it like I do, but because there's a lot of fractions going on here and a lot of substitutions, I don't like doing all that in my head and writing out the expression. Some students do. I tend to make mistakes when I do that. So I did the substitutions in for dq and r squared here. And then I just put the little dot for that's not dot product. We're not doing dot product of vectors. It's just multiplied by, and then I make this substitution, which I know is y over the square root of x squared plus y squared. Now I look at this equation. The only thing, the dx, I'm going to be integrating with respect to x, because I got a dx there. The only thing now, the only variable in that equation that changes is now x. Right? There's no theta there. There's no r there. The other k doesn't change, lambda doesn't change, it's uniform, y doesn't change, so we're good to go. And I can actually simplify this.
What you definitely could just plug the thing into the calculator if it's on like an FR2, and then instead of like having to simplify from there.
Yeah, you probably could. Unless you need to find the expression for the electric field, not just the answer.
And it'd be annoying.
But I don't know, your calculators are so fancy now, they probably can do that.
Or just write it like that with all the values in the variable.
Well, if they only wanted DE, you could write this.
Like-
But we want E. We want to do the integral. And to do the integral, we're going to have to simplify this, as you'll see.
Okay.
So DE, so to simplify this, and you should have the math skill anyway. You're going to be expected to when you get to college. I'm going to use the associative commutative property here to get dx on the end. So I have k lambda y dx over, how can I rewrite this denominator? What's x squared plus y squared quantity times the square root of x squared plus y squared?
X squared plus y squared quantities.
What's that?
Quantity of x squared times plus y
Oh,
squared times the square root. Isn't it?
I can write it with this, a single power.
It is.
3f's? Yeah. This is x squared plus y squared to the 1 power. This is x squared plus y squared to the 1/2 power. X to the n times x to the n is equal to x to the n plus n. Right? You just add those exponents, 1 plus 1/2 is 3f's. And then I have a nice expression that has x in it, dx, so now I can integrate both sides. And then we run into a problem. First of all, I'm going to integrate my limits negative L over 2 to L over 2. When I integrate when I add up all of the electric fields, DEs, I just get the total electric field, which is what I'm looking for. And I can drop the y subscript because all the x components cancel out. So when I calculate the net electric field in the y direction, I'm actually calculating the net electric field. and that's going to be, there's a lot of constants here, right? K is a constant, lambda is a constant, y is a constant. I can pull those out. So I have k times lambda times y times the integral from negative L over 2 to L over 2 of dx over x squared plus y squared to the 3 halves. And if you could do that integral, you're a better mathematician than I am. Because you haven't learned how to do that yet. And you won't until you go to college. And most people won't actually learn how to do that integral. People much smarter than I have done all kinds of integrals like this and put them into tables. And they will literally call it that sometimes. Integration by tables. You look up, if you see an integral of this form, you look it up in a book or in a calculator, and it will give you the result. So if you have a problem like this on the AP exam, and you come to an integral that you won't learn how to solve in your calculus class in high school, and if you do know how to solve that, then more power to you, then they will tell you, integrals of this form give you this result. And so you just look it up. It'll say, like, look up in a table of integrals or something like that. And so when you do that, you'll see, and I don't even have this memorized, because if you have anytime you have an integral of dx over some constant squared plus x squared to the 3 halves, the result will always be x over a times the square, that's the constant, times the square root of a squared plus x squared, obviously plus c at the end. Right. So if you got to this integral when you're doing this problem on the AP exam, this would be given to you. Okay? Or maybe a few of them, and you'd have to come up with this and then decide, oh, this is the one I got to choose. You aren't required to go from here to here. Okay? I don't know how to do that. Ms. Fudge probably would be able to, but I don't know. But I noticed that this has that same form. Yes, the x's are in different positions, but the denominator is the variable squared plus a constant squared raised to the 3 half powers with just a dx in the numerator. What that tells me is I can use this information to write that the electric field is therefore, and it is a definite integral because I have limits, so we can drop the c there. The electric field will be k lambda times y, and then I've evaluated this integral just by looking it up in a table, so it'll be times x over, what takes a's place in this? Y, times the square root of y squared plus x squared, evaluated from negative L over 2 to L over 2. I just did that integral by looking it up. That's totally fine. Totally fine. A lot of physicists, when they come up with these nasty integrals, they're like, I don't want to deal with that. I'm going to look it up in a book or ask my mathematician friend, and they'll tell me.
I feel like school always sets you up. Like in elementary school, I was like, yeah, you're gonna have to write cursive and everything in middle school and high school. And you're not gonna be able to use calculators. You're gonna solve everything by hand. And then the more advanced you get, it's like, yeah, use a calculator, look it up, Google it, whatever.
Not always. This, only when it's like beyond your level. You encounter it, but it's beyond your level. And that happens to professional physicists. Like you said, they'll get to a math problem. They'll be like, well, the physics tells me that this is what I got to deal with, but I don't know how to deal with it. But I know there are people that do, so I can just give them a call because they work at the same university, you know.
That's how computer science is. Like computer programming is less about memorizing how to do certain things. It's more about learning how to learn how to do things. Like
Yeah.
learning how to Google what you're trying to do.
Yeah. All right. So let's evaluate this. This is where it can get a little tricky. And now I got to evaluate this expression from at these limits. So the net electric field is going to be k times lambda times y times, I plug in L over 2 for x, L over 2 over y times the square root of y squared plus x squared. That'll be L squared over 4, right? Under the radical, right? And then I subtract the negative, I'm going to run into this. Subtract, evaluating the limits of integration, I subtract always, but then I have a negative L over 2 over y times the square root of y squared. And it is negative L over 2, but that gets squared, so it's going to be plus, again, L squared over 4. Right? So I have a negative and a negative, so I'm going to end up adding L over 2 plus L over 2, which gives me 2L over 2, which gives me L. So I have, L in the numerator over this. So when I evaluate that, I end up with K lambda times Y times just L over Y square root of Y squared plus L squared over 4. And again, I have this expressed in terms of charge density, and I really want to express, yes, we have a charge density here, but if we have a certain amount of charge that we know it resides on that rod, then we can get an actual numerical value for the electric field, not by putting in the charge density, but by putting in the actual amount of charge, the total amount of charge, so I can replace lambda with just Q over L, right? So I'll say that the electric field then is just going to be K times Y.
Take out a Y while you're at it.
Oh yeah, thank you. I have a Y and a Y, so those cancel. So I'll have K times, instead of lambda, I'll put total charge over length. And then I have times length over the square root of Y squared plus L squared over 4. And the L's cancel. And so I get that the electric field will be K Q over the square root of Y squared plus L squared over 4.
It'll be like half the AP exam. So we spend a long time.
Yeah, this is no joke. It's no joke.
Well, it makes sense why the L wouldn't matter, because no matter how long the pole is, it's always going to be canceled out in the next direction.
Yeah,
It still matters.
smart.
Matters a little bit.
A little bit.
I left something out. There's something
The
going.
pole's feelings matter, I know. But
Hiding somewhere in the numerator.
You don't matter if we just divide you into
Oh, it
that's
does,
a
yeah.
small piece.
Oh, I feel like I missed something.
Maybe you did. Maybe
You
you
missed one of
This
these.
is, oh, my bad. Yeah, something was wrong here. The units wouldn't have worked out. So what I was talking about at the beginning of class wouldn't have happened. This is A squared. You guys forgot. When you looked up in that table of integrals, that's supposed to be A squared.
Yeah. So Timothy, you're wrong. You can't just cancel the Y.
So that's Y squared. So only one of those Y's cancels. You realize that the units wouldn't have worked out, right? It wouldn't have been the same unit. So we actually do still have a Y here. Because the square root of these guys gives us a length. We got to multiply that by another length in order to have a length squared in the denominator. All right. And if I wanted to write that as a vector, in this particular coordinate system, it would be positive J hat. Here's my electric field. Notice you got a K and a Q in the numerator, and you got a length squared in the denominator. There's some interesting stuff that can happen. What if
Well, elementary.
rod was infinite length?
Doesn't matter.
Well, the equation will actually change a little bit. Because essentially we're saying the electric field, if it's at an infinite length, will be the limit as L approaches infinity of KQ over Y times the square root of Y squared plus L squared over 4.
So that-
And as L approaches infinity, what can I replace the denominator here with? What can I get rid of?
Everything and replace it with infinity.
Well, I can just get rid of Y, right? The Y under the radical, I can get rid of Y because it's inconsequential in terms of as compared to L squared over 4.
The square root of infinity.
This one isn't. Let me, because we're running out of time. This one isn't as interesting. Let's say, what if Y. Let's say Y approaches infinity because I'm running out of time. What if the distance Y approaches infinity? This is the interesting one. Then I'll say, all right, well, the electric field then will be the limit as Y approaches infinity of KQ over Y times the square root of Y squared plus L squared over 4.
Would it be 0?
still be zero.
Let's say as we just get far away, real far away, but not all the way far away. You'll see what I'm saying in a second. So as y approaches 0, L squared over 4 becomes, there's more rigorous ways of evaluating this limit, but for the sake of time, L squared over 4 becomes inconsequential, right? Can we see that?
Yeah.
So not infinitely far away, but as we get farther and farther away, the value of L squared over 4 becomes less and less important. And there will be a distance where we still have electric field, but the value of L squared over 4 is so small in relation to y squared that it doesn't even matter. And so we can kind of rewrite this as the
Wouldn't L squared be getting larger, and then because dividing by that, the electric field will get smaller?
No, it's going the other direction.
Yeah. Ignore what I was saying about the rod being infinitely long. Let's go back to the regular rod, and we're getting infinitely far away. And so the electric field then will be kq over y times the square root of y squared. Well, what's the square root of y squared? Kq over y squared. Which is the equation for the electric field due to a point charge, right? And so that should make sense, because the farther away you get from this rod, the more it's going to behave like a point charge, because its dimensions aren't going to matter as much. Right? So it's just interesting. You're probably not going to have to do that, but it's interesting to note. Yes, this isn't the true way of evaluating that limit, but so don't show that to Miss Fudge. And if you do, tell her that Gianni told you that. Okay.
You were like, well, whenever it gets close to infinity, but close enough or far enough away, where it's not infinity.